Hi, this is Mr. Roy. I'm going to take you through this gas stoichiometry problem. This is one that we've done in class. And so this particular question talks about having some natural gas undergoes combustion. So just a couple things. I would not require or expect you guys to be able to do maybe this entire reaction right off the bat, but eventually this is something you'll definitely need to do. So combustion, means that we're taking our CH4 and we're going to react it with some oxygen. And when you react a hydrocarbon with oxygen for combustion, you get two products, and the products are carbon dioxide and water. So now that we have the reaction written out, at this point, maybe on the test, I would expect you to pick it up and be able to balance this reaction. So the first thing we need to do is make sure that we have the same number of each type of atom on both sides of the reaction. So if you look here, we have one carbon and we have one carbon over here. We have 4 hydrogen. You always want to save the oxygen to last, or the hydrogen and oxygen to last. In this case, the oxygen will be the very last. We have 4 hydrogen on this side, so in order to get 4 hydrogen on this side, we have 2 right now. We want to put a 2 in front of the H2O. Now the hydrogens are balanced, so the last thing is to balance the oxygen. If we look here, we have 2 oxygen in the carbon dioxide and 2 times the 1 oxygen in the water. That would get us to 4 oxygen total. So on this side, what we'll do is we'll put a 2 in front of the O2. So now that we have a balanced reaction, we can deal with the rest of the stoichiometry to solve for this problem. So, we're given 45 liters of natural gas. We're also given the pressure and temperature that the gas is at. So what we need to calculate out in order to be able to use this balanced reaction is the number of moles of gas. So we're going to plug into Pivnert our values. We know that the volume is going to be 45 liters. We know that the pressure is going to be 730 atm. And in order to use our gas constant, we're going to need to change this from millimeters of mercury to atm, and we do that by dividing by 760, and we'll get a value there, and we'll get that in a second. We know the temperature is 20 degrees Celsius, which we will convert to Kelvin by adding 273. And then we'll plug all these values into Pivnert, and we're going to take our PV is equal to nRT, and we're going to solve for N by dividing both sides by RT. So that cancels that, and N is equal to PV divided by RT. And so if we plug this all into our Pivnert equation here, again we get the pressure to be 0.96 atm. We solve for N and we get 1.8 moles of methane gas, CH4. Sorry, that's supposed to say moles here, but alright. And that's CH4, sorry. Now that we have it in moles, what we can do is we can use the coefficients from the balance equation to solve for each of our products. So if we start with our known value of 1.8 moles of CH4, we can solve for the amount of carbon dioxide. So what we would do is, we would say that for every 1 mole of CH4, how many moles of carbon dioxide would react. And if you look up here, there is no value in front of CO2, just like there's no value in front of CH4, so that counts as 1. So we're going to say it's a 1-to-1 ratio of carbon dioxide to CH4. And then the next step is, in this case we want to solve for grams of CO2, so we need to know what is the mass of 1 mole of CO2. And so what we would do is we look on the periodic table, we'd find that carbon has a mass of 14 grams, we'd find that oxygen has a mass of 16 grams, and in this case there are 2 oxygens in carbon dioxide, so that comes out to be a total of 44 grams. per 1 mole of CO2. And if we multiply through, we would find that there are 79 grams of CO2. And then we're going to do the same thing solving for water. So again, we do 1.8 moles of CH4. Then we look at the ratio of CH4 to water, and we say that there are 2 waters for every 1 CH4. And then lastly, we multiply by the fact that 1 mole of water has a mass off of the periodic table of 18 grams. 2 for each of the hydrogen, or excuse me, 1 for each of the hydrogen and 16 for the oxygen. And then we will multiply through, and we get 64.7 grams of water. So that's how you solve for grams based on this gas stoichiometry problem.